Hello, this is Shushmita and welcome to the Physics Cafe. Today we are going to learn about units and measurements. In today's session, which is the first session of this topic, we are going to talk about the need for units, the different types of units. We are also going to discuss about dimension, the dimensional analysis, and what are the limitations of dimensional analysis. We are going to solve a lot of problems for easier understanding. We are also going to solve problems from previous year's questions of IIT JEE and NEET and other such entrance examinations. The question that first comes to mind is, why do we need units? I will go ahead with a very practical example that we face in our day-to-day life. Suppose you want to buy a t-shirt. So you go to Flipkart, you browse through a lot of t-shirts and you choose 2 t-shirts to order from. Now you already have a t-shirt at your home which is a medium size. So you order 2 medium-sized t-shirts of 2 different brands from Flipkart. Once they are delivered and you try it on at your home, you realize that though one of them fits you, the other one doesn't. The reason behind that is this: if you check their size chart, you will realize that though you have ordered the same size, which is medium for both the company, but their standardized size is 38 cm for one t-shirt and for the other one it is 40 centimeters. So medium here is not a standard unit of measurement for the size of your t-shirt. If you had used centimeter to measure the width of your t-shirt, then you would have got the correct size for yourself. In our everyday life, we use many such units for our purposes and needs. Suppose you want to buy rice from a grocery store. How will you ask the shopkeeper? You'll ask him to give you 1 kg of rice. Here kilogram, which is also an SI unit. So in this chapter, we're not going to learn anything that is out of our practical or everyday life. We use these SI units and many other units in our everyday life for our day-to-day needs and purposes. Moving on further, though there are units that have been invented, but different parts of the world, the different countries, many of them use a separate system of units and they have their own conversion formulas for conversion from one system of unit to the other system of unit. But as we advanced, there was realized a need to standardize the system of units throughout the world, and for that a general conference was called upon, a general conference of weight and measures to standardize the units, and we got the SI system of units or the International System of Units. Let us look into the 3 different types of units that were used before the standardization of the system of units. One is the CGS system of units, which was widely used in different parts of the world, like it is also called the French system of units. It was originally invented by a German physicist. The FPS system of units, however, was used in countries like the United States of America, Liberia and Myanmar. In this FPS system of unit, length is measured in terms of foot, pound is the unit for mass, and second is the unit for measurement of time. Similarly, in the MKS system of unit that comes from the name meter, kilogram and second, length is measured in meter, mass is measured in kilogram and time is measured in second. Similarly, in the CGS system of unit, centimeter is used to measure length, gram is used to measure mass and second is used to measure time. In the further examples of the class and the problems that we will solve, and in the convention used throughout this course, we will mainly use the SI system of unit, though we will learn problems of conversion between different types of units as well. In the SI systems of unit, there are 7 physical quantities or 7 base units that are defined for 7 physical quantities. 3 of them, we have already discussed about 3 of them, and those are length, mass and time. Meter is the unit for length, kilogram is the unit for mass, and second is the unit for time. The other 4 base units are temperature. For temperature we are using Kelvin, for electric current we are using ampere, for luminous intensity we are using candela, and to measure quantity of matter we are using mole. There are 2 other units that are called supplementary units that are defined in SI system of units. One is the plane angle, the unit for which is radian, and solid angle that is measured in terms of steradian. Let me give you an example. Suppose a particle is moving. Suppose a particle is moving in a circular path, and at an instant of time t, say it is at point B, and it is moving like this in a anticlockwise motion. After some time t plus dt, the particle reaches the point B. So this radius is r, and the position A and B, the angle that it creates at the center of the circle theta, is called a plane angle, and it is measured in terms of radian. This is a 2-dimensional motion. If this motion happens in 3D, we are talking about a sphere here. This angle will become a cone, and this angle is called a solid angle, which is measured in terms of steradian. It may appear to you that why not use a single unit for the measurement of the similar type of quantities. Like if we are to measure length, why not use a measure for all the measurement? Why not use meter for all the measurement? The reason behind this is that if you want to measure the size of a bacteria, using meter would be meaningless, because bacteria fall in the size of 10 to the power minus 6 meters. So this 10 to the power 6 term will appear to be much more vague if it is given in terms of meter, rather than we should try to give it in terms of microns. Similarly, if we are to measure the distances between two, say, railway stations, it will be meaningless to express it in terms of centimeters. We should be using kilometers to express this kind of a measurement. Similarly, if we are to measure the distance between Earth and Sun, then kilometer would be a much lesser unit. Let us dive right into the first problem of this session. It is given that the surface tension of water is 72 dyne per centimeter. Converted in SI unit. Dyne and centimeter. This means it is in CGS system of units, and we want to convert it to the SI system of unit. We know the dyne in the CGS system of unit is the unit for force, and the unit for force in the SI system of unit is Newton. So what we know is that we have to convert 72 dyne per centimeter into 72 into some multiplication factor Newton per meter. So we have to find out this multiplication factor that will convert from the CGS system of units to the SI system of unit. Let's start. We know that force is equal to mass time acceleration, which is mass times the change in velocity. The change in velocity is again the change in displacement per unit time, or the change in the distance traveled per unit time. Therefore, the unit for force comes out to be gram into centimeter divided by second square in the CGS system of unit. We want to convert this quantity into the SI system of unit. What we know is that 1 kilogram is equal to 100 grams. 1 kilogram is equal to 1000 grams, or 10 to the power 3 grams. 1 meter is equal to 100 centimeter, or 10 square centimeter. And second remains the same. So gram centimeter per second square. This converts into 10 to the power minus 3 kilogram into 10 to the power minus 2 meter divided by second square. So it is 10 to the power minus 5 kg meter per second square, and this quantity altogether is called Newton. So 10 to the power minus 5 Newton. Next on, our dyne is converted to Newton, which is 10 to the power minus 5 Newton. Now it's time to convert the centimeter into meter, which is again 10 to the minus 2 meters. So altogether it is 10 to the power minus 3 Newton per meter. So here we write 10 to the power minus 3, or which can be written as 0.072 Newton per meter. So finally, our 72 dyne per centimeter converts to 0.072 Newton per meter in SI system of units. That is our final answer. Hope it is clear to you. We'll move on to our next problem. Let us see what is given. The normal duration of ISC physics practical period in Indian colleges is 100 minutes. Express this period in microcenturies. They have given what 1 microcentury is. 1 century means 100 years, and micro is 10 to the power minus 6. So 100 into 10 to the power minus 6, or 10 to the power minus 4 years. Let us convert this to minute. 1 year consists of 365 days. Each day consists of 24 hours, and each hour is consisted of 60 minutes. So if we reverse this, we will get 1 minute is equal to 10 to the power 4 divided by 365 into 24 into 60 microcenturies. If we want to convert 100 minutes to microcenturies, we will get 10 to the minus 4 into 100 divided by the same factor. Let us calculate this. So it is 1.9 microcenturies. And this is our answer. The next question is, how many microcenturies did you sleep yesterday? So if you have slept for say 7 hours, then again you'll have to convert that hours, then you'll have to convert the microcenturies into hours. So you can ignore this part here. You can simply do 10 to the minus 4 into 365 into 24 hour. So 1 hour would be 10 to the power 4 divided by 365 into 24 microcenturies. You can multiply this with the number of hours that you have slept and you'll get your answer in terms of microcenturies. Moving on, we will see that for the same unit, we have something that is called the prefixes. What is the need for that? Suppose the SI unit for length is meter, but we want to measure the size of a bacteria, which I already told you is of the order of 10 to the power minus 6 meter. In that case, instead of using this factor 10 to the power 6 again and again, we can simply use the word micro or micron. Similarly, if we want to measure the size of an atom, which is of the order of 10 to the power minus 10 meter, we can drop this factor and we can use the unit, that is Armstrong. If we are to measure the size of the nucleus and express it in terms of meter, it would come as 10 to the power minus 15 meters. We can again drop this factor and use and represent our measurement in terms of Fermi. Or femtometers. There are some other interesting units. Let us talk about time. Usually in SI system of units, we are representing time in seconds. But if we are to represent the distance between our galaxy, our sun, and say the nearest star, which is Proxima Centauri, we use the expression light year. What is light year? It is the distance that light travels in 1 year. So it is velocity multiplied by time, and the speed of light is 3 into 10 to the power 8 meter per second. And the time, that is 1 year, which has 365 days. Each days have 24 hours, each hour have 60 minutes, and each minute have 60 seconds. So this huge length is expressed in terms of light year, that is used to measure the astronomical distances. A much larger unit is called parsec, which is 3.26 light year. Moving on further, there are two types of units. One is the fundamental unit. We have 7 fundamental units in the SI system of units and 2 supplementary units. The rest of the units can be derived using these 7 fundamental units, and those units are called the derived units. I'll give you one example. The example of one of the fundamental units is length. The unit used to express a measure length, let us say in the SI system of units, it is meters. Now if we want to calculate the unit for volume, a volume is nothing but length cube or meter cube. So it can be derived from the 7 basic units. If we are to derive the unit for speed, which is length per unit time, it will come out as meter per second, which is again, the second is again one of the 7 base units defined in the SI system of units. So all these units like meter per second, the one we used in one of our recent problem, which is Newton, or the one we used in the CGS system of units such as dyne, this all can be derived from the 7 basic units defined in the SI system of units and are called derived units. Let us look into this problem. It says the equation of state for n moles of an ideal gas is PV equal to nRT, where R is constant. The SI unit for R, they want us to calculate the SI unit for R. They have given us PV equal to nRT. Therefore, R is nothing but PV divided by NT. We can do it in this way. We can write the unit for pressure, which is nothing but force per unit area, and the unit for volume is meter cube. The unit for N is number of moles and that of temperature is Kelvin. Now force is Newton and area is meter square mole into Kelvin. So this becomes Newton into meter divided by mole into Kelvin. Newton meter is nothing but force into displacement, which is the unit for work, and the unit for work is joule divided by mole into Kelvin. So it is joule per mole per Kelvin. So option B is correct. We can also look at this problem. We can solve this problem in another way. I'm going to discuss about it now. The average energy E is expressed in terms of 3 by 2 RT. So this is the average energy, means energy per mole. We can write R from here as E divided by NT. Energy is in joule, N is in mole, and T is in Kelvin. So this is a much shorter way. We are not using the equation that is given in the problem. We are using some other equation that we already know, and we are getting to the result in much short span of time. Moving on further, we are talking about dimension. For the 7 fundamental quantities that we discussed about earlier, 7 unique dimensions are associated with them. For length, we write it as L. For mass, we write it as M. Similarly, for temperature, we write it as K. For time, we are writing it as T. For electric current, we are writing it as A or alpha, and for amount of substance, mole, and for luminous intensity, we are writing it as C. Though in many of the problems you will see this is written as I, you should not be confusing it with anything else. We will fill up this table by the end of our discussion, and you can memorize this table for solving your problems in a short span of time. I will not recommend memorizing everything. Let us first understand how we can derive the dimensions for force and how the dimension for thrust and tension are similar as that of force. So as we know that force is equal to mass times acceleration, and acceleration is change of velocity, which is again, this quantity is again distance per unit time by time. So it becomes ml. divided by t square, that is equal to ml t to the power minus 2. That is the dimension of force. Now thrust is nothing but the force applied perpendicularly to a surface, and tension, as we know for an example, if we suspend a metal ball from a rope, the force that acts on the rope upward by virtue of the weight of the metal ball that acts downward is called tension. So it is also a kind of force. So all of the three quantities, force, thrust and tension, have the same dimension, that is ml t to the power minus 2. Now let us see the dimension of work. Work is nothing but force into displacement. Force is ml t to the power minus 2, as we have already deduced, into displacement has the dimension of length L. So work has the dimension ml square t to the power minus 2. Energy is same. Energy is obtained by a body by virtue of its work, so they are the same quantities. Let me write it down, and now we will move on to see the kinetic energy. The equation, that the simplest form of equation that we know is half mv square. M has the dimension of mass and v is L by t whole square. So ml square t to the power minus 2, which is again same as the dimension of work and energy. Let us now look into the dimension of moment of force or torque, which are the same quantities. If there are two forces that are acting parallel but in opposite direction, then that force multiplied by the perpendicular distance from the point of application of the force is called torque. Suppose this is the point O, and along this point of application two forces act in opposite directions and they are equal. So torque is equal to this force into the perpendicular distance, which is nothing but again force into same as force and displacement. So ml to the minus 2 into L, which has the same dimension. Next comes the angular momentum. To simplify, we have our xy coordinate and we have our r theta, or the circular coordinate. Xy is the two-dimensional linear coordinate and r theta is the two-dimensional angular coordinate. In the linear coordinate we express displacement as x, and in angular coordinate we express displacement as theta. Velocity is expressed in the linear coordinate as x by t, and in the angular coordinate as theta by t. The momentum is nothing but mass times change in velocity, which is mass mx by t, and the same quantity in the angular coordinate. Mass is replaced by moment of inertia and the velocity is replaced by omega, which is theta by t. So I is again summation m into k square. K has the dimension of length and omega. So m is mass, L square, omega is theta by t. Theta is a quantity that is dimensionless, so we can write 1 and divided by t. So t ml square t to the power minus 1, and that is the dimension for angular momentum. Let us check if it is true for Planck's constant as well. The simplest equation is equal to E equal to h nu. That is the energy equation. H is equal to E divided by nu. Nu is frequency, which has the dimension 1 over time period, so 1 by t, and energy is ml square t to the power minus 2 by t. So it becomes, the t goes above and it becomes ml square t to the power minus 1, which is same as that of angular momentum. Pressure is equal to force per unit area, that is mlt to the minus 2 by L square. So ml to the minus 1 t to the minus 2. Let me write it down and then we will check for stress. Stress is the force per unit area that is needed to create a deformation in the body, so which essentially have the same dimension as pressure, which is force per unit area. Now looking into the energy density, which is energy per unit volume, ml square t to the minus 2 by L cube, that gives me ml to the minus 1 t to the minus 2, which is again the same. Let us now look into the modulus of elasticity, which is stress divided by strain. Strain is a dimensionless quantity because it is the ratio of two similar quantities. Therefore, the modulus of elasticity has the same dimension as that of stress, which is again ml to the minus 1 t to the power minus 2. The next quantity that we are going to look into is the surface tension, which is force per unit length. So ml t to the power minus 2 divided by L, which is mt to the power minus 2. Spring constant F is equal to kx. K is the spring constant, which is again force divided by x. That means the dimension of force divided by length, which is same as ml t to the power minus 2 divided by L, again m t to the minus 2. The surface energy is ml square t to the power minus 2 per unit area, which is L square. The L square cancels out and give us the same result. Let us now talk about momentum and impulse. The simple equation that we know for momentum is the mass times the change in velocity. So mass into velocity is L t to the power minus 1. Similarly, impulse is nothing but the force that acts for a short period of time. So ml t to the minus 2 into t, which again gives mlt to the power minus 1. So both of them have the same dimension, and that is mlt to the power minus 1. Looking further, angular velocity, which I have told earlier that in angular coordinate, this is also called the circular coordinate, in which the displacement is expressed in terms of theta and the velocity is expressed in terms of omega, that is theta by t. Theta is a dimensionless quantity and this becomes 1 by t. So angular velocity is nothing but t to the power minus 1, same with frequency, which is equal to 1 by time period, which is 1 by t or t inverse. Resistance, reactance and impedance. Let us go to a blank page to understand these three quantities. The simplest equation that involves resistance is V is equal to I into R. We know that work done to move a charge Q in a potential field difference of V, Q into V is equal to the work done. So the dimension of V is the dimension of work done divided by the dimension of charge. We know that current is charge flow per unit time. So charge is nothing but current into time. So the dimension of charge is the dimension of current, which was defined as A in the SI dimensional quantities, but I am taking it as I, and for time it is T. The dimension of work done or energy is mL square T to the power minus 2. So mL square I to the minus 1 T to the minus 3. This is the dimension of the potential. So R that is equal to V by I is m L square I to the minus 1 T to the minus 3 divided by I, which is m L square I to the minus 2 T to the minus 3. So it becomes m L square I to the minus 2 T to the minus 3. Reactance and impedance is nothing but a representation of resistance in a circuit that involves a capacitance and an inductor. So the reactance, the capacitive reactance, which is 1 over 2 pi F into C, and the inductive reactance, which is 1 over 2 pi F into L, are another representation of the same quantity, which is R, also for the electromagnetic wave in space. A quantity that is equivalent to resistance is defined as a root over mu naught divided by epsilon naught, which also has the dimension of resistance. And that is called impedance. So let us write here mu naught by epsilon naught root over. So let us deduce the dimension. That was we deduced the unit for R. We are now going to deduce the dimension of R. So again, writing down this equation, we get R is equal to E by N T. Energy is m L square T to the power minus 2 divided by T, which is m L square T to the power minus 3. This is the dimensionless quantity. What about the Boltzmann constant? It also belongs to the same equation as energy, where R by N is replaced by K. N is again a dimensionless quantity. Let us now look into two interesting quantities, that the permittivity epsilon and the permeability mu. For free space, they are written as mu naught and epsilon naught. 1 over mu naught epsilon naught is equal to the speed square of speed of light, that is 3 10 to the 8. And root over mu naught by epsilon naught, which is called the impedance, which is an equivalent of resistance for electromagnetic wave through free space. We will now get into deducing the dimensions of epsilon naught. The easiest equation that we know about is electric field is equal to 1 by 4 pi epsilon naught Q by R square. Let us make it much simpler. The force on a particle of charge Q due to Q1 due to the electric field created by a particle of charge Q2 is this 1 by 4 pi epsilon naught Q1 Q2 by R square. So the dimension of epsilon naught is equal to the dimension of charge square, the dimension of force, and the dimension of R square. I have told you that charge is equal to current into time. So I square t to the power minus 2. I square t square divided by ml t to the power minus 2 multiplied by L square, which comes out as m to the power minus 1 L to the power minus 3 I square into t to the power 4. This is the dimension for epsilon naught. Let us now look into the dimension for permeability in free space, that is mu naught. The easiest equation that we know is the force between two current carrying conductors per unit length is mu naught by 2 pi I1 I2 divided by d. This d is the distance. This is also the dimension of distance, so they will cancel out. So the dimension of mu naught is equal to the dimension of force divided by the dimension of current square, which is ml t to the power minus 2 divided by I square. That comes out as ml t to the power minus 2 and I to the power minus 2. Let us now deduce the dimension for this quantity, which is 1 over mu naught epsilon naught. I have already told you this is equal to the square of velocity of light. Velocity means length divided by time, so L square t to the power minus 2, and that of impedance of electromagnetic wave in free space is equal to that of resistance that we have already deduced earlier. What is the physical use of the dimensional method? Suppose there is an apple at this height and it falls from this point here to down here, and this height, we call this height as h. We want to deduce the time taken by the apple to fall from point A to point B, or the time taken by the apple to traverse a distance of h. Now, using our basic knowledge, we know that this time will depend obviously on the height. It will also depend on the mass of the apple, and it will also depend on the gravitational pull with which Earth attracts the apple downwards. So let us say it depends on gravitational acceleration. We do not know by which amount the time depends on these three quantities. So let us assume that this time is proportional to the eighth power of h, bth power of m, and cth power of g. Now we will use the dimensional analysis to get to our result. Height has the dimension of L, mass is m, and the gravitational acceleration, which is Lt square. So L to the power C t to the power minus 2c. So L to the power a plus c m to the power b and t to the power 2c is equal to time, which has the dimension of time. We equate both of the sides as there are no quantity of L here. That means L to the power 0 is equal to L to the power a plus c. So a plus c is equal to 0 or a is equal to minus c. This is our number 1 equation. Secondly, simply b is equal to 0 because there is no quantity of m over here. So b is equal to 0. Third, the power of time 2c is equal to 1 over here. So c is equal to minus half, which gives us, using this equation, a is equal to half. Now we know that this time depends on h as half, on m as 0, and on g to the power minus half, and that becomes h by g root over. Instead of using the equal to sign, here let us take a proportionality constant. So it is some constant c multiplied by root over h by g. Let me write it down somewhere over here. We got some constant c root over h by g. Now I'm going to use our knowledge of one-dimensional analysis to reduce this equation. Apple falls from the height h and it takes time t. It falls from rest, so the initial velocity is 0, and the time it touches the ground, let us say the velocity is v. So using this equation, is equal to ut plus half a t square, we get h is equal to 0 plus half g t square. So t squares becomes 2g by h, or t becomes root over 2g by h. So our proportionality constant over here is equal to root 2. Let us conclude our class here. In our next class, we are going to solve a lot of problems that were asked in the previous years in IIT JEE and NEET from unit and dimensional analysis, and later on in our further sessions, we are going to learn about use of vernier calipers, screw gauge. We are going to learn about significant figures, rounding of numbers, and error calculation, and we are going to solve a lot of problems from there. See you in the next session. Till then, take care. Bye bye.